Welcome to the Introduction to Data Structures and Algorithms. In this session, we will understand the importance of data structures and algorithms, often abbreviated as DSA, in computer science and software development. So, what exactly is DSA? DSA is actually the combination of two things. First, data structures, which are ways to organize and store data efficiently. Think of them as specialized containers that hold data in a specific format, like a list of names or a collection of product details. Second, algorithms, which are step-by-step procedures or sets of rules for solving problems or performing computations. Imagine a recipe. It lists the ingredients and step-by-step instructions to prepare a dish. Similarly, an algorithm provides a sequence of instructions for a computer to accomplish a specific task. Now let's explore why DSA is so important. It helps in efficient problem solving, enabling you to choose the right tools for specific problems, leading to more effective solutions. It also helps in performance optimization, allowing you to create faster and more efficient software systems that utilize resources effectively. It leads to better code quality by helping you write cleaner and more maintainable solutions that are easier to understand and modify. It is also an essential knowledge for career advancement, especially in technical interviews, where DSA skills are highly valued by top companies. Let's explore some core data structures that every programmer should know. First, arrays and lists. These are sequential collections of elements accessed by an index or position. They are fundamental for storing collections of similar items. Second, linked lists. These are linear collections of elements where each element points to the next, enabling efficient insertions and deletions. Third, stacks and queues. These are collection types with specific access patterns, last and first out respectively, ideal for managing ordered operations. Fourth, trees and graphs. These are hierarchical and networked structures representing complex relationships between elements. Let's delve into hash tables and maps. Hash tables and maps are data structures that store key value pairs with efficient lookup operations. They offer an average time complexity of big O of 1 for search, insert, and delete operations, making them incredibly fast. They use a hash function to map keys to array positions, allowing for quick access to values. They handle collisions, which occur when different keys map to the same array position, using techniques like chaining. They are essential for implementing dictionaries and caches, enabling rapid data retrieval. Now let's discuss algorithm fundamentals. First, searching algorithms. These algorithms are used to find an element within a data structure, like an array or a list. The common types are linear search, which checks each element sequentially, and binary search, which uses divide and conquer approach but requires sorted data. The time complexity for linear search is big O of n, while for binary search it is big O of log n. Second, sorting algorithms. These algorithms arrange elements in a specific order, such as ascending or descending. Examples include bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. Their time complexity can range from big O of n squared to big O of n log n, depending on the algorithm. Third, graph algorithms. These algorithms process interconnected data represented as graphs. Common examples include breadth-first search, depth-first search, and Dijkstra's shortest path algorithm. The time complexity can range from big O of v plus e to big O of v squared, where v is the number of vertices and e is the number of edges. Fourth, dynamic programming. This approach is used to solve complex problems by breaking them down into smaller, overlapping subproblems, solving each subproblem only once and storing the results to avoid redundant computations. It is applicable to problems with overlapping subproblems and optimal substructure property, and typically involves memoization and tabulation techniques, which can reduce exponential time complexity to polynomial time complexity. Now let's understand time and space complexity. Time and space complexity are ways to measure algorithm efficiency in terms of time, which is the number of operations required, and space, which is the amount of memory used. Big O notation, such as big O of n, big O of log n, and big O of n squared, is commonly used to express the upper bound of an algorithm's time or space complexity. Time complexity refers to the number of operations an algorithm performs as a function of the input size. Space complexity refers to the amount of memory an algorithm uses as a function of the input size. Analyzing time and space complexity involves considering average, best, and worst-case scenarios, as well as understanding the trade-offs between time and space. Now let's talk about algorithm implementation. Translating algorithmic concepts into working code requires careful implementation. To achieve this, start with a clear understanding of the problem, making sure you know exactly what you are trying to solve. Choose appropriate data structures based on the requirements of the algorithm and the nature of the data. Handle edge cases, which are unusual or extreme input values, and validate inputs to ensure your algorithm behaves correctly under all circumstances. Optimize after getting a working solution, focusing on correctness and clarity first before attempting to improve performance. Test with various input sizes and scenarios to ensure your algorithm is robust and handles different situations gracefully. Let's explore an effective problem-solving approach to tackle any coding challenge. Step 1. Understand the problem clearly. Define the problem, identify inputs, outputs, constraints, and edge cases to ensure you have a solid grasp of what needs to be solved. Step 2. Plan your approach. Design your solution, choose appropriate data structures and algorithms for the task at hand, considering their trade-offs and suitability. Step 3. Implement your solution by writing clean modular code. Focus on readability and correctness before worrying about optimization. Step 4. Test your solution thoroughly. Verify your solution with various test cases, including edge cases, and analyze its time and space complexity to ensure it meets the required performance criteria. Step 5. Optimize your solution. Refine your solution by looking for better algorithms, data structures, or implementation improvements to enhance its efficiency and performance. To continue your DSA journey, here are some valuable resources and next steps. Explore online platforms such as LeetCode, HackerRank, and CodeSignal for coding challenges in practice. Utilize interactive DSA visualizations to gain a deeper understanding of data structures and algorithms. Leverage open-source algorithm libraries to learn from existing implementations and contribute to the community. Read books such as Introduction to Algorithms, also known as CLRS, and Grokking Algorithms for comprehensive coverage of DSA concepts. Consider taking online courses and specializations on platforms like Coursera and Udacity to gain structured learning experiences. As for the learning roadmap, first master basic data structures like arrays, linked lists, stacks, and queues. Second, understand time and space complexity to analyze algorithm efficiency. Third, learn fundamental algorithms such as searching, sorting, and graph traversal. Fourth, practice with coding challenges on platforms like LeetCode and HackerRank. Fifth, apply your knowledge to real-world projects to gain practical experience. Sixth, dive into advanced topics such as dynamic programming and advanced graph algorithms to further expand your skills. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.